If you recall, we've been working on integration by substitution, and in a traditional sense, in my tradition, we spend way too many days talking about integration by substitution because it's so cool. But I don't want to assign just a random selection of substitution problems. I want to go set up a sequence of problems that have some kind of purpose to them. So once again, I'm going to be using this x squared plus 1, and then we're going to start making adjustments to the x squared plus 1. So realize that all the examples up to this point have been focused on using this x squared plus 1. And then yesterday we did some changes with reading cosines or reading powers of trig functions. So today we want to emphasize the main point. We're trying to figure out what substitution we want to make and what other parts we need to make that substitution work. So once we decide on what our substitution is going to be, we have to be aware of what our DW needs to be to make that substitution work. What do we want to do and what do we need to make that go? So we've got this nice straightforward problem here, the integral of x times the square root of x squared plus 1 to x. So in this problem, we see the square root function with an x squared plus 1, and we see the x on the outside. What we're trying to develop is the vision. See that x squared plus 1 as the substitution that we want to make, and see that the x on the outside of the radical is there to be the DW. And that makes this a nice standard problem. Then we also want to continue. The third thing that we want to read is the function we're actually integrating, and that's the square root. So we're going to be integrating a square root of w, or a w to the 1/2 power. So we have 2/3 w to the 3/2. We're going to have an extra factor of 1/2 because the derivative of the inside is 2x, and we're going to have to cut that in half. So we can see right away that this is going to be a 1/3 x squared plus 1 to the 3/2. We want to be able to write down the answer by identifying those three parts and knowing what's going to happen. Let's write down the details to make sure that that happens. The substitution that we want to make is the x squared plus 1. It's our best candidate. It's actually inside. There's a composition of functions, and this is the inside of the square roots. So this means that our outside function, the thing that we're actually integrating, is a square root function. If w is x squared plus 1, then dw is 2x dx. So to make this substitution go, I don't care about the 2, but we do need that factor of x. And like we said earlier, we have that. That's the whole reason that I put the x out there. I like to take out the 1/2, so to remind myself that I only have that extra factor of half of the dw. And that shows me that the x dx is the thing that I need to make this substitution work. X dx is what I need to make x squared plus 1 equal to w. Then we are ready to write our w integral. I've got a 1/2 from the half dw. The function that I'm integrating is a square root. X squared plus 1 is the w, and then I could just finish writing the dw at the end of my integral. So here the x dx is equal to 1/2 dw. As we predicted, the thing that we're actually integrating is the square root function. So it's going to be 2/3 w to the 3/2. So I still have this 1/2 from my dw. Integrating the square root function will be a 2/3 w to the 3/2. And since we've integrated, this is when our constant of integration shows up. So there we are integrating the square root of w and w to the 1/2 power. We add 1 to the exponent, divide by the new exponent. The 1/2 was there because of the dw. So we could simplify that and replace w with our expression in x. The goal is to skip writing the details down and just notice what the details are going to tell us. So this detail here is telling us where this 1/2 came from. This 2/3 w to the 3/2 is us recognizing that once we replace the x squared plus 1, we're going to integrate the square root of w. The goal is to look at this integral, and the only thing that we write down is the answer. Do not pass go or collect $200, go directly to the end. That's the goal. You might not be there yet, but that's what you want to practice. That's what you want to have in mind when you're practicing. Any questions? How's everybody okay? Is substitution just too easy? Is that it? Let's continue on this square root theme, but I'm going to start changing the inside. I know we're all getting tired of seeing this x squared plus 1. It's just so useful. We learn all about the x squared plus 1, then turning that into some other quadratic with complex zeros is not much of a big deal. We understand how this one behaves, and we can see how all of them behave. We need to categorize things. But I'm going to change the inside. The inside is going to be an x to the 4th plus 1. And right now you're like, oh, dude, that wasn't much of a change. And I'm like, oh, I know. But it's a small progressive of kind of obvious changes to make. That's how we start seeing the pattern. Now, right now, we don't know what to do. Right now, this is not a substitution problem. What do I need to make this a substitution problem? What am I trying to get you to substitute? What is your W here? X to the 4th plus 1, and that's sitting in a square root, because I can't change everything about a problem. I change one thing about the problem, but what am I going to need to make that substitution work? I have to put some stuff out here. What do I have to put out here? X to the 3rd, perfect. I need something to be the DW. If I don't have that X to the 3rd out there, this is not a substitution problem, and we'll have to do something else. 4x to the 3rd would work as well. That would be everything what we need. But the bare minimum would be at least the x to the 3rd with our easiest constant, 1. Our easiest constant that doesn't just wipe everything out like 0. So that's what we need to make the substitution w equals x to the 4th plus 1. To make that substitution go, my dw is 4x to the 3rd dx. So in this case, I have a 1/4 dw is x cubed dx. If I had a 4x to the 3rd out in front, I wouldn't need that 1/4. But the constant factors, we can adjust to the constant factors. The important part was x to the 3rd. We needed that to make an x to the 4th substitution go. Now we're ready to substitute. Here, we're still working on writing out our details because it's still only like the first couple of days of substitution training. So notice that we ended up with a very similar W integral that we had before. But where before we had a 2x dx and we divided by 2, producing that 1/2. Here, the derivative of the inside was a 4x to the third. And so we ended up, our W integral had a constant of 1/4. That 1/4 follows along when we integrate. But the integration part is the same. There's still a 2/3 W to the 3/2 power. So here, 1/4 of the 2/3 is going to be a 1/6. And we have x to the 4th plus 1 to the 3/2. First step is deciding what substitution we want to make. That leads us to the second thing. What's our outside function? What are we actually going to be integrating? And our third thing, the dw. What's our dw? What do we need to make that substitution work? Is everybody okay? Easy enough? Too easy? Is there ever such a thing as too easy in a math class? Or am I called, oh, here's your midterm, and like there's like one problem on it. It's like it says 2 + 3. If you got a midterm in Calc 2 and it just said 2 + 3, would you just be suspicious and think there's something going on? Like, oh, 5. Wait a second. What base is this problem in? And then like, oh, base 10. And you're like, oh, wait a second. What if you're just altering reality so that when you say 10, you actually mean it's in base 4? Sorry. I don't know. I didn't leave enough space. It's fine. I'll write small. Let's suppose that we have this square root of x squared plus 6x plus 13. Once again, I want to be integrating a square root function. And if you're paying attention, notice that this problem is the same as the problem that we had two examples ago. I just traded my x squared plus 1, the most basic of quadratics with complex zeros, for something else with different complex zeros. But the question is, what do we need to make this a nice, boring substitution problem where I'm just integrating a square root? I'm trying to set this up where w is equal to x squared plus 6x plus 13. And so our f prime, the thing that we're actually integrating, is a square root function. So what do I need for a dw? 2x plus 6. My DW is a 2x plus 6. And since there's more than one term in my DW, I'm going to wrap it in parentheses. This only makes sense if the 2x plus 6 is all being multiplied by the dx. It doesn't make sense to have a 2x plus just the 6 times dx. No one would think that, but we're going to try to build good habits and put parentheses around factors with more than one term. And I definitely need those parentheses up here. Whoops. What are we going to have to do? Did I break the problem by writing x plus 3? Can we fix this? Yeah, I just take out a 2. So I'll just divide by 2, and 1/2 dw is an x plus 3 dx. So once again, I wrote the problem with the minimum amount that we need. I need to have an x plus 3 to make that substitution work. Once we make that substitution, now our w integral is the same as the one we had before. So it's going to be a 1/2 integral of square root of w and a 1/2 dw. That was a little bit of a cheap tactic to just switch to a different parabola, but I wanted that extra constant in there to recognize that we need that constant in there. We needed to have an x plus 3 to be the dw. Notice that the style of setup we're using today is a little different than yesterday. Today, I want you thinking a little bit more about how the problems are built so that you can recognize what to do. That will improve your understanding of how the process works. So that once we get through this class, we never have to do this process again. Well, I'm not supposed to say that part out loud. Yes, because in the future, when you're working at Lockheed Martin and building spaceships to fly to Mars, you're going to have to do integrals by hand. Wait, maybe that's not the case. I don't know. I'm kind of tired of justifying everything in the future. I was told so many times in my algebra classes and my trig classes, I'm like, oh, man, why do we have to know this? And I was told a couple of different common answers that you get when you're in high school. You're going to need this in calculus. And like as a teenager, you're like, oh, so you're telling me that if I avoid calculus, I'll never have to do this again? And the teacher's like, oh, well, touche. Or probably my favorite response, shut up, please. To which I was like, oh, fair. That's how high school is supposed to work. Got it. The important thing to do when you're working on these problems is to not just assume that everything is going to work out just fine. Know what you need to make your substitution work. Know why you need that stuff to make the substitution work. Don't just figure that everything will be fine. Seems reasonable is never good enough. This is the curse that you're placing on yourselves by choosing to go into science. Seems reasonable is not okay. Anytime someone's arguing something, they're like, well, doesn't that seem reasonable? You have to stop. And now you have to consider this person's motivations. Now you have to understand where they're coming from. And you can't get that from them. You can't trust them because they just tried to seem reasonable at you. You go, well, doesn't that seem reasonable? That person is not your friend. They are trying to manipulate you. Remember, my friends are like, oh, please, doesn't that seem reasonable? I'm like, oh, well, I don't know. Now I need to know your motivations. They're like, oh, well, here are my motivations. So I go, no. I don't need to hear what you think your motivations are, or more importantly, what you think you want me to think your motivations are. I need to actually know what they are, and I will determine that by your actions. So you can just shut up and I will observe you. You know what I mean? You have to know how the stuff works. I know most of you are going to be engineers and you're going, no, we just have to know that it works. But no, you have to know how stuff works. And that's why we're getting into the weeds and spending too much time doing integration by substitution. It's also just fun, right? So we have to know when stuff is going to work and we have to know when stuff ain't going to work. So we got to mix today. If I had this integral set up with the square roots of x squared plus 6x plus 13, any multiple of x plus 3 will make the substitution work like we did in the previous. But if all we have is something other than x plus 3, then a multiple of x plus 3, let's say like just plain old x, we can't make this substitution work. It's not enough. This substitution isn't good. dw is 2x plus 3 dx, and x is not a multiple of this. X is not just a constant multiple of 2x plus 3. Oh, 2x plus 6. This doesn't mean that we're totally stuck. It just means that this is not going to be a plain old run-of-the-mill substitution problem. More importantly, it means this substitution is not going to work for us. So whatever we're going to do, it's not going to be this substitution. To make that substitution work, I need a constant multiple of 2x plus 6 to be the dw, and we don't have that. I can't be subtracting stuff. I only get to multiply, and this is not good enough. Any questions? You have to know how substitution works. You have to know when it's not going to work. Don't just assume that it's going to work. Oh, the x is out there to be the derivative of the inside. Everything's going to be fine. And then people be like, oh, well, what about the plus 6x? And you're like, oh, I'm just going to ignore that and hope everything works out for the best. So I call this next couple of examples stupid substitution tricks. This goes back to Dave Letterman's old show where they had stupid pet tricks. No one's seen that for a long time, but for some reason it just kind of stuck. So I still call them stupid substitution tricks. This is not in the category of stupid substitution tricks. We're going to do a modification of this. That is kind of a stupid substitution. Notice that we're still displaying the square root of stuff there. So in this problem, we've got a very simple substitution. It's harder to spot in the beginning because there's not something on the outside to be the derivative, not something, not the derivative of the inside is harder to spot. Here's why the derivative of the inside is harder to spot. And here's why every example today has been a square root one. That's to make sure that you're thinking of square root as the outside function and priming you to say W equals the inside. So I go this way. If I had opened up with this problem first thing, then we might not have seen it. But since all the other examples have been square root of W, you're kind of primed to think about x minus 3 should be the W. See how I programmed you? Have you heard about the clapping along thing? What did I just clap? The song, what was it? It was Happy Birthday. What was that one? You can't hear it, right? Happy Birthday is a little bit easier. Open with that one, but then switch to something that's a little bit less common, but still kind of recognizable, but not recognizable, right? That's what this problem is. If I opened up with this problem, that would be like clapping a song you didn't recognize. But since every example has been square root of W, you're kind of primed to be like, oh, well, I'm going to make W equal x minus 3. If W is x minus 3, what is dW? Just 1. Cool. Do we have that? Yeah. All we need is a constant and a dx. We've got a constant and a dx. And our outside function is still the square root. So yeah, this is nothing fancy going on here. It's a little bit harder to spot if we hadn't been doing this all day. But there's our square roots. There's our W. And dx is our dw. All that's going on here is we're shifting. W and x are just horizontal shifts of each other. That's why the substitution is so simple. We didn't have to stretch anything out. I only recently heard about the clapping thing, which was a really interesting study that was done. I guess it was a long time ago. I didn't pay attention to that part. Because there was a study that was done. And maybe I was interested. It was funny that came along because it was a couple of months ago. I had texted my friend by saying, hey, do you recognize this song? And I texted the sounds that I made to make the song. I wanted to see if he would recognize them. And he didn't. So the question came across my mind. It's like, oh, can you text someone a song without like the lyrics? Because if I did the lyrics, then he would have got it right away. Like, well, what if I text the way that I hear the opening to Ghostbusters? Will he recognize it? The answer was no. I'm going to modify this one because all these substitution problems are all about taking something and modifying it. Right now, you're thinking, dude, that has not been modified. But now it has. So this one definitely looks very different because we are prime thing square root of W, but then there's this extra X out in front. So here's what's going on here. We're primed to think that our W is an X minus 3. To make that work, we need a dW of 1 dx. And we've got that. We've got the dx right here. We've got the W here, and our inside function is just a square root. But all these x's have to go away. I have to translate from integral in x to an integral in W. So we need to deal with this x out in front. We need to deal with this x. Everything else can be accounted for. I've got a dw. I can make my substitution x minus 3 for w. My dx can be the dw, and I'm integrating a square root function, but then I've got this x out in front. That has to become w as well. In this case, there's no trick to it. It's just a simple trick. We can, because the x and the w are both the same degree, it's just a horizontal shift. I'm going to shift this problem from an x integral to a w integral. I can rewrite w equals x minus 3 as x equals w plus 3. This seems like a strange thing to do, but it's going to do something very important for us that we have to be able to recognize. So my integral is going to have these parts to it. This x becomes a w plus 3. The square root of x minus 3 becomes a square root of w. My dx gets traded for a dw. And we finished our lateral shift, our horizontal shift. Take everything, move it 3 units left. This is why that matters. Now the exponent on the 2 terms is 1. In the original, the exponent on the 2-term factor was a 1/2. That's a problem. Exponents don't distribute over sum. But on this w integral, the 1/2 power is on 1 term. That is the thing that we've gained. Oh, yeah, that's fine. That factor with 2 terms now is degree 1, whereas before the factor with 2 terms was degree 1/2. Degree 1/2 is a problem because I can't take the x and put it into and distribute it inside and separate terms. But now that the factor with multiple terms is degree 1, we can distribute and separate into terms. This is what we gain by making this substitution. Now I can distribute this w to the 1/2 power and separate into terms. So I could write this as the integral of w to the 3/2 plus 3w to the 1/2 dw. Because now we can just separate it into terms. The integral of w to the 3/2 is 2/5 w to the 5/2 plus 3 times the integral of w to the 1/2, which is 2/3 w to the 3/2. And then we can just replace the w's. Any questions? You jump on to Wolfram Alpha, this is not what you'll be looking at. Wolfram Alpha will definitely simplify this in some fashion. But it'll simplify it in some weird AI style fashion. Now that I see all these computers making AI art and writing AI papers, I can see why Wolfram Alpha's expression choices are a little bit strange. When I see the weird AI art, read the weird AI papers and the way things get phrased, I now have a clearer understanding of why Wolfram Alpha and the TI-89 have the weird syntax that they do. Sometimes, not always, sometimes. I realize now it's just the uncanny valley of mathematical syntax as interpreted by where computers are trying to emulate the human. Pretty dope. Any questions? This is a super substitution trick. It's just kind of a horizontal shift. This one was a nice simple horizontal shift. The point was we had two terms with a 1/2 exponent, which is inconvenient. So if we shift things over, then we'll get two terms with a degree of 1 so that we can distribute. The goal was to write powers of x. If we can write powers of x, then we should write powers of x. 2/5 comes from taking the w to the 3/2 and adding 1 to the exponent. 3/2 plus 1 is 5/2, and then dividing by the new exponent. 1 divided by 5/2 is 2/5. I really look stunned. There's too many examples. Or is it just too easy? I'll go with 2 easy. We'll have a major exam tomorrow. I'm just kidding. Put your stuff away. We have a major exam right now. I'm just kidding. No one has time for that. We have to make sure that we have all the parts in play to make things work. Now here, we had this horizontal shift. The reason that this horizontal shift was simple was that I have x to the first outside, x to the first inside. They had the same power, so I could shift where that square root landed. So then the question becomes, what if I should have gone with the plus one and one? That's squared minus 3 is just. That's what I want. Can I do the same trick on this and horizontal shift? More importantly, why can't you just do the same trick on this? So that is the question for today. Why can't we just horizontal shift this one like the last one? And then the follow-up, what is the smallest thing that we could do to fix this one and make this one horizontal shift like the last one? So I've just gone from x squared of x minus 3 to x squared squared of x minus 3. And I've told you that we can't do the same horizontal shift that we did in the previous one. And I want to know why that is. Then I want to think about what's the least we could get away with to make this one work like the previous problem. How can we take this and turn it into just a slightly less basic problem than our original? And then I could be disappointed that I didn't time this to end with an x squared plus 1 like we started with, after promising you to get rid of the x squared plus 1 in all the problems, and then only to have it come back later, supervillain style. Any questions? All right, certainly answering this question right now would clear a lot of things up and go a long way to making you understand integration by substitution much more clearly, but only if I explain the answers to these questions right now. But you could probably tell that these are the two questions that I'm definitely not going to be answering today. So that's going to do it for today. I'll see y'all on tomorrow. Everybody have a good day, and thanks for playing.